Tappenden. Paul and I have been talking about the Everett interpretation for about 40 years. Strangely, we seem to have drifted further and further apart. These things happen.
And got closer together at the same time in a funny sort of way.
That's right. There are ways in which... anyway, so, Paul, the floor is yours. Thank you.
Okay, well, thank you. Hello, everybody. And especially to Lev, Toda, for the opportunity. So, for the sake of efficiency and hoping that this will give rise to some discussion, I'm going to just read something which I've prepared in advance, and it'll only take about 15 minutes. The title then is Making Sense of Everettian Fission Without Self-Location Uncertainty. Lev and I have our differences about many worlds, but we've long had in common is the fission interpretation of branching. The idea in Everett's notorious footnote that observers can split into multiple futures which are all actual. That's opposed to the overlap interpretation introduced by Simon Saunders and David Wallace in 2008, and the divergence interpretation introduced by Simon in 2010. There's some dispute over whether or not the overlap and the divergence interpretations are equivalent, but for both, observers don't split. Observers inhabit worlds where a single outcome is inscrutably determined in advance. Prior to a quantum measurement with multiple outcomes, the observer inhabits one of a multitude of parallel worlds with a range of futures corresponding to the possibilities. On making the measurement, the parallel worlds partition into branches which include all those worlds where a particular outcome occurs, and that partitioning corresponds to the unitary evolution in such a way that the branches can be assigned quantum amplitude. Prior to measurement, the observer is uncertain as to where they're located, whether they inhabit a world where this or that outcome will occur. And it's argued that they can assign degrees of belief relative to the various futures equal to the squared amplitudes of the branches. Lev was the first to explicitly apply the concept of self-location uncertainty to Everettian theory, but it wasn't pre-measurement uncertainty because he was thinking in terms of fission, where the observer believes that all outcomes will occur in their future. He introduced the concept of post-measurement pre-observation uncertainty. David Albert complained that Weidmannian uncertainty comes too late, if it comes at all, but I argued in a 2011 paper that the very possibility of Weidmannian uncertainty is enough to provide reasons to accept pre-measurement wagers in the same way as for pre-measurement uncertainty. However, a problem for fission remained. If Everettian theory is to make any sense at all, the blindfolded observer on a post-measurement branch must assign degrees of belief as to which outcome has occurred in their vicinity equal to the squared amplitudes of the branch. But why should the observer do that? Lev has given reasons, but they've not found universal acceptance. I've argued for a different reason. The absolute square of branch amplitude, call it branch weight, can be strictly identified with objective probability. The argument is in the paper to which my poster refers, and I'll put the poster up tomorrow. The title of that paper is Pilot Wave Theory Without Non-Locality, and I propose a version of many worlds which includes hidden variables but differs in a fundamentally important way from interacting worlds theory. Here I'm just going to argue that the idea of identifying branch weight with objective probability isn't as unintelligible as it may seem. The thought that quantum processes could be stochastic is widespread and is generally accepted as intelligible even if not true. Stochastic theory posits objective probabilities. Uncertainty prior to measurement is explained in terms of what's become known as the principal principle, which is basically the idea that the observer should assign degrees of belief in outcomes equal to what they take the objective probabilities of those outcomes to be. We have as yet no justification for the principal principle, but in the context of stochastic theory, it's taken to be sufficiently obvious to warrant its use. For stochastic theory, an actual outcome is randomly selected from a range of possibilities, where the randomness is constrained by the probabilities. But if I believe in fission, and I believe that branch weight is objective probability, and I use Lev's quantum Dye world splitter, then I must be certain that all outcomes will occur, not just one, together with being certain that the probability of 5 occurring is a sixth. Doesn't that involve a contradiction? No. For if all 6 outcomes will occur, then that entails that 5 will occur. The future occurrence of 5 does not entail that the probability of its future occurrence is a sixth. But, you might say, if the objective probability of the occurrence is 5 is a sixth, then I should use the principal principle to assign a degree of belief of a sixth to the future occurrence of 5, not certainty. So it would seem, but here the principal principle is overruled by logical consequence. Again, we don't have a justification of the principal principle. We simply take it as obvious in the context of stochastic theory, where we've only ever employed it when thinking in terms of alternative futures. We've also taken it to be obvious that the future occurrence of an event entails that the probability of its future occurrence is 1. And we've just seen that that's not necessarily the case. To repeat, if I'm certain that all outcomes will occur, I must be certain that 5 will occur, even if I believe that the probability of the future occurrence of 5 is a sixth. This is a counterintuitive and a bit quick, so I'm going to describe a thought experiment which can help to make what I've said more transparent. But first, I have another disagreement with Lev, which I need to mention. When he uses his world splitter, he believes that he will have 6 successors seeing different numbers. But his successors aren't him. So should he expect oblivion? Personal fission poses a problem which Derek Parkett famously wrestled with a few decades ago. It's a problem that mustn't be ignored if a fission version of many worlds theory is to be made fully coherent. Happily for fission theory, a resolution of Parkett's problem became available in 1996 with Ted Sider's seminal paper, All the World's a Stage. Temporal counterpart theory, which is what Sider proposed, remains marginal in discussions of persistence, but it's not met with any objection more serious than that of being out of kilter with common parlance. It proposes that Lev is indeed not his successors, but they can be construed as being amongst his future temporal counterparts, which entails that Lev bears a relation will be to each of them. Contrariwise, each of his successors bears a relation was to Lev. Temporal counterpart theory permits persisting persons and objects to have dendritic, partially ordered histories, as well as conventional, well-ordered histories, which are linear. At any given moment, an observer is identified with a momentary temporal part of their history. So now for the thought experiment, and I'll just adjust this a bit because I have to bend down. Whoop. You'll be familiar with the idea that our environment is causally isolated from more distant parts of the universe, and that we have no evidence that space is finite. Our Hubble bubble is known as the observable universe and has a radius of about 46 billion light years. So there could be a countable infinity observable universes indistinguishable from our own. Max Tegmark has calculated their average separation as being around 10 to the 10 to the 117 meters. So Everett aside, our local environment now could be just one of an infinite number of parallel worlds. Suppose that Lev's quantum die isn't a world splitter at all. Suppose it's stochastic. When you click on the button, only one of 6 equally probable possible outcomes occurs. That entails that the infinite set of parallel worlds partitions into 6 subsets, call them branches, where each of the outcomes occur. The subset measures of the branches are necessarily a 6th, because what it means for an outcome to have a stochastic objective probability of a 6th is that the subset measure for that outcome on a sample tends to a 6th as the sample tends to infinity. The subset measures of the branches are the objective probabilities of the different outcomes. These are not Everettian branches, of course. They're branches of a partitioning infinite set of erstwhile parallel observable universes, which are being presumed stochastic for the sake of argument. At this point comes a change of perspective. We drop the common assumption that there's a one-to-one correspondence between observers and Doppelgänger. We suppose that an observer is more like a novel than a book in which it's printed. Okay? 2 copies of the same novel. There's one novel, no matter how many copies of the book. One novel, so long as there's at least one book. This is the unitary interpretation of mind, which I've defended in several papers. It requires using set theory in an unusual way. You no longer inhabit one of a set of parallel worlds, you inhabit the set. Your body is an infinite set of doppelgangers. Its mass is a mass which the doppelgangers have in common. Your location is an infinite set of elemental locations, elemental in the set theoretic sense. Lev's quantum die now becomes a world splitter, not for Everettian reasons, but because it's an infinite set of elemental stochastic dice. When you click on the button, you fission into 6 observers, each of whom you will be. Their bodies are infinite sets of elemental bodies whose subset measures are a 6th. You know that you'll be observer seeing one of 6 numbers, each of which has an objective probability of future occurrence of a 6th. So what do you expect to see? Now you can follow the stochastic theorist's use of the principle without fear of contradiction. You assign degree of belief a 6th to the seeing of each of the numbers because the objective probability of the branch on which each number occurs is a 6th. You're uncertain about what you'll see in just the same way as you would be if you believed that you inhabited an observable universe which is not a set and that Lev's die is stochastic. You're not uncertain in the sense that you will be one or other of your future temporal counterparts. You will be each of them, each seeing a different number. Pre-measurement uncertainty about outcomes is a cognitive state of assigning partial degrees of belief to multiple futures. For stochastic theory, where futures are construed as alternative possibilities, it's generally regarded as acceptable that the pre-measurement uncertainty should derive from applying the principle. What we have seen is that pre-measurement uncertainty can be derived in a similar way for Everettian fission, so long as our future coexistent actualities can be assigned objective probabilities. A strange consequence of the foregoing setup is this. Each of these books, each of these books has a mass of 150 grams. So the set of the two must be a book which has a mass of 150 grams. That third book has indefinite location since each of its elements has a different location. If I were to throw these two books, I'd feel the inertia of 300 grams, not 450. So where is that extra 150 grams? Imagine that there are isomorphic rooms, one on my left and the other on my right, outside the auditorium, if you like, containing matched doppelgangers. The set of the two rooms is a room inhabited by Diana, whose body has the doppelgangers of subsets, each doppelganger being an infinite set. We put each of the books in corresponding places in each of the rooms. When Diana throws her book, the two doppelgangers move in synchrony so that the two elements of Diana's book follow twin trajectories. So Diana throws the book, and the books follow twin trajectories like that. When Diana throws the book, which is the set of these two books, she feels the inertia of that extra 150 grams. I can't feel the inertia of the third book because I can't interact with it. To do so, I'd have to take Diana's place, for which I'd need a machine which could cause my body to fission. It would require an input of energy at least as great as my body mass, so a very different process would be involved than for Everettian fission. My poster goes a step further. We replace the hypothetical set of stochastic worlds with a set of pilot wave or interactive world. There comes to be a sense in which we inhabit configuration space. This book becomes an infinite set of books which includes all the possible particle configurations which could constitute something isomorphic to this book. There we are.
We've got lots of time for discussion. Well done.
I was a little confused about the mass of these things. I mean, if this is Everett splitting, the whole space-time split. So of course you don't have twice as much mass and after the splitting. I mean, each universe has the same, mass energy is locally conserved, and so that's, if it's asymptotically flat, you'll have the same mass before as after. Did you mean Everettian splitting or something else producing
what I've presented here is a sort of experiment which sort of paves the way to what I sort of explain in the poster and the paper which goes with it, a paper which is was published by Foundations of Physics a few days ago. And that's the paper which is about pilot wave theory without non-locality. So here, what we've got is just the idea, we've got this cosmological setup where we've got, we think of ourselves in one observable universe, but there's a countable infinity of them. And now the change of perspective involves this reinterpretation of the relationship, if you like, between mind and body. I mean, it's not a dualist idea at all. It's simply the idea that normally we think we've got a whole load of doppelganger in different worlds. There's one observer, one subject for each doppelganger. We drop that idea and say, that's why I was using the books, that what it's like, an observer is more like the novel than the book in which it's printed, right? Now, to get that idea to work, what I've had to do is introduce I use set theory and I explain why in the paper. But what that set theory involves, I mean, normally we think of sets as abstract objects, right? So I'm saying that, and I'm talking about the set of these two books being a physical object. A physical object which has, and this is what we need to get this interpretation of the mind-body relation to work. The set has the properties which the elements have in common. There are a few exceptions, but so the set of these two books has a mass which is the same as the books, what the mass that the books have in common. So the set is a third book, and it's here in this room, and it's got a mass of 150 grams, and it has indefinite location because they're not at the same location. I can't get these two books into the same location. So, I mean, does that answer your question? That's the way that the theory works. That's it.
Each book has how much mass, and then?
Well, each book has got each book has got a mass of 150 grams, right? Okay. Now, normally we talk about the set of these two books, and we think of it as an abstract object. Now, what I'm suggesting is we can think of it as a physical object, and it's a physical object which you can only interact with if you're like Diana in the two rooms, having a subject who has got a body which is two Doppelgänger, yeah? You know, what I was suggesting to you is, in the thought experiment, is instead of thinking yourself now as inhabiting one of these infinity of observable universes, you now inhabit the set, which means that your body is an infinite set of bodies which are physically isomorphic, right? And each has a mass of whatever the mass of your body is, and your body has that mass because that's the mass that they have in common.
Okay, but I mean, if there's a different different observable universes within a vast spatial universe,
yeah.
I mean, then if both bodies exist, if the two bodies exist, then in some sense, well, you don't really have the mass of a closed universe. But I mean, suppose for simplicity it is asymptotically flat, but you have these two parts, and they each have a 150 kilogram mass, then the total mass contributed by these would be 300 grams, because they're both in the same, if they're both in the same universe.
Yeah, but the thing is,
branch, right? I mean, it's just two different observable universes, right?
Yeah, and the thing is that with the change of perspective, what we call this observable universe is the set of all those isomorphic. They're no longer out there in the distance. They're all here, which means that beyond it is vastly indeterminate. But
yes, if you're talking about two subjects as different books of the same novel, but I'm sorry, it would seem that after having different experiences and probably branching to more and more different experiences, we have two different novels.
absolutely. So that's why you get the vision. Remember what I was saying is you're in this situation. We've got these parallel worlds, and you inhabit this set of parallel worlds. You use Lev's quantum splitter. What happens? Your body, which is a set of an infinite set of body, it partitions into 6 subsets. Each of those subsets is the body of a different person. They're Lev's successors. Huh? They're the people who you will be. They're the observers who you will be, each one seeing a different number. So yes, absolutely. As soon as there's a cognitive difference between these bodies, the subject splits. That's the idea.
Also about the mass, you have a problem there because you have, okay, two people, okay, two macroscopic objects. Now, in one universe, one of them emits an electron. In the other universe, the other guy accepts an electron, absorbs an electron. Okay, so right now, the mass is different.
Yeah,
So what's the mass of the set?
Well, it becomes indefinite because the masses of the elements aren't the same. The set only has definite properties when its elements have exactly the same property. So as soon as there's any difference in properties of the elements, then the set comes to have an indefinite properties. It will have an indefinite mass between having one electron more or one electron less. So it'll be, quite precisely defined, but still a little bit of indefiniteness.
Thank you.
Just at the technical level, what do you want to do about singletons? I mean, if
Oh, okay, good. Okay, so I go into this in quite a lot in the paper, but in fact, I mean, this idea of construing sets as physical objects, the first step in that direction was taken by Quine. He introduced the idea of what's is known in sort of logical circles as a Quine atom. And so if we're thinking of individual physical objects, he identifies it as being a self-membered set which is identified with all its unit sets. Yeah.
yes, but I mean, what about if sets are physical objects? I mean, if X and Y are physical objects, then the set X, Y is supposed to be a physical object.
Yeah.
How about the singleton of X, Y?
That would be the aggregate of X and Y.
Right, but now I want its singleton.
What's that?
Now I want its singleton.
Well, okay, so I've got X and Y each as a singleton. I've got the aggregate, the mereological sum is a singleton which has the mereological sum as an element.
My concern is you're imagining your two books, and then the set that consists only of the two books, and I'm to think of that as a physical object.
Mm-hmm.
And I'm now interested in the singleton of that set.
Well, okay, I've got the aggregate of these two books, and the singleton is the set which has the aggregate as its sole element.
Okay, but I'm getting confused now, because there's obviously a strategy you could run which involves taking aggregates or mereological sums or something, but I didn't think that was your strategy. I thought you were taking sets to be these.
I am, but I would I'm distinguishing between the set of these, which is a book which has got indefinite location, and the aggregate.
Okay, so I'm definitely talking about the set, not the aggregate. So take that set, the set that has the two books as elements, which
Yeah.
we thought about as physical and definite.
Right.
Now take the singleton of that set. And my thought is, I'm interested. If that set, if the set of the two books is a physical object, then it's going to be, then it would seem that.
Well, okay, yeah, I see what you mean. What I'm doing is following Quine on identifying the unit, the units, the singleton, its unit set, and its unit set, and unit set as all being the same thing. Yeah.
Right, but Quine only makes that identification for elements.
Absolutely.
Sets, but this is a somewhat stronger claim.
Absolutely. It's the suggestion
And is that consistent?
it's a suggestion that we can go further and say that that any set of Quinean individuals is also a physical object. Yeah.
And therefore identified with its own single.
Yeah.
And is that provably consistent? I mean, equiconsistent.
I'm assuming it, and that's an assumption in this interpretation of the mind-body relation. Yeah.
I mean, let me suggest that's a technical project that needs to be done because, I mean, you know, we know something about the consistency of Quine's framework relative to things that are consistent. I think.
Good. Right.
I think if you want to make that move, I don't see any obvious reason it wouldn't be, but these things get tricksy, so it's probably worth actually checking.
Okay. Right. Thanks.
Suppose we have two observers in identical rooms and they've each picked a card from a deck and haven't looked at it yet. So
I'm sorry, I can't quite hear. Is it switched on? That? Yeah.
suppose that we have two copies of a person in identical rooms. They've each picked a card from a deck and they haven't looked at it yet. So they have different cards, but they don't know what the cards are. So are those, do you think of those as the same person or two different people?
Ah, good. Okay. So, so long as the Doppelgänger in the two rooms, they remain physically isomorphic, then we've got one subject. So that's interesting because it's like Lev's post-measurement, pre-observation observer. The idea that we would have one observer until a moment in which they turned the cards over or they became somehow aware of the difference, in which case you'd get different cognitive states and you get the fissioning of the observer into two.
So you're actually saying that the post-measurement pre-observation actually does not exist in your system because you consider them the same person still at that point.
Yeah. So what happens in that situation is that you've got the two branches, and you've got the single observer who is effectively inhabits both, right? So which means that their environment is in superposition, or it's in an indefinite state. I don't want to talk about superposition because in terms of the cosmological example, it would be an indefinite state. So in other words, here I am, I've done the measurement, or I've turned the cards over, but I've selected cards, but I haven't looked at them yet. Then I'm in a situation where the card in my environment, which is the set of the two cards, is in an indefinite state relative to me, right? So it means, and in the quantum mechanical concept, it means that for Lev's post-measurement pre-observation observer, in effect, what they have in their environment is macroscopic superposition. Yeah.
Well, may I just understand if you distinguish between two cases? I showed two cases. In one case, there is observer beyond the wall, and there was a measurement, and there are two words, A and B, but the observer is just, the wave function of the observer didn't change. And from my point of view, in this situation, there is no any self-location uncertainty, there is nothing, he belongs to both worlds. And there is another case in which I'm asleep and I'm moved to different places, and when I'm awake, I see the same environment, but there are two different me, one in one room and that one in another room.
Right.
So then, do you consider the difference, and in which case, because you use this term of objective probability, which I never understood. I'm trying to say that many words and objective probability. There is many words that A happened and B happened. Where is objective probability? For objective probability, you need A or B. And in both cases, there is both A and B.
Yeah, so the point of the run-up was to sort of explain that there doesn't need to be, there's no contradiction between saying that there two things are going to occur in the future and they both have probabilities less than one. that was what I meant when I was saying you could be certain that all outcomes will occur, and also certain that the probability of outcome of 5 was a 6. But the thing is, Lev, when you talk about being in two worlds at once, I've just got a different way of saying that. I just say what you have an indefinite state in your environment. You see, how can one observer be in two worlds at once? I say, well, you've got one observer and their environment is an indefinite state. So if you've got A in one branch and B in another, then I've got in my environment something which is neither A nor B. It has an indefinite alphabetic state, if you like.
Again, we have to kind of, at least, I'm trying to find the semantics for many words and define what the words are.
Right.
And if I perform a quantum experiment and get different macroscopic recording, for me there are two words. So there is word A and word B. There is no anything not definite. There are definitely two words. Still, it might be in this word there is an observer who doesn't know and he belongs to two words. I don't see any contradiction. But the whole idea of many words, that everything is completely definite. There is no everything deterministic and definite.
Okay,
And the way to make it, I just use semantics. By definition, in a word, nothing can be indefinite. Because word, this is my definition in a word, and something became indefinite, I will say, oh, now there are more than one word.
I'm in conflict with your definition, because I'm saying that in a world you can have indefinite states. But so, look, we do something. We've got the two branches, two different worlds, and we've got in those worlds we've got the two Doppelgänger, right? And the whole point about this idea about the relationship between mind and body is that those two Doppelgänger are the elements of the body of one subject until such time as there's a cognitive difference, and then they come to inhabit each of the worlds. Until that time, they sort of straddle the two, if you like. That's the idea.
Let me just conclude with a question that I think people were a little surprised with your conclusion. You went to many pilot waves theory set up. Could you just explain why you chose to do that rather than going to the Everett interpretation? Why go to many pilot wave theories?
Well, because I think the criticisms of the idea that a pure wave theory is adequate, I've come to believe that's not. It isn't adequate. It's not adequate for the sake because of the sort of reasons that Valia was talking about. I know that in sort of work that you've done and Lev has done with the sort of center of mass arguments, you talk about sort of being able to get a sort of a 3D configuration of objects from the wave function, but I don't think it goes down to what we need to do is get down to the microscopic level, and you can't do those sort of arguments for electrons. And so, I sort of, I really had a very sort of dog-legging in my thinking a couple of years ago, because I gave a talk to a group who had sort of pilot wave enthusiasts in it, and when I was talking to them, somebody came up and said, oh, what you're talking about is a many pilot waves theory. And I thought, blimey, I hadn't really thought of it like that, but it seems to me that doing it in terms of the many pilot wave worlds theory, you can combine the best of both, and the result is, and actually, this is what I argue in the paper. As I said, the title is Pilot Wave Theory Without Non-Locality. You meet the pilot wave theorist demands to have particle trajectories, and you do it in a way which conserves locality. And in fact, you do it in a way so that in our environment, if it is indeed a set of pilot wave worlds, in our environment, particles don't follow trajectories, because in each of these worlds, the relevant particles are following different trajectories. And because you're taking the particle which is in your environment is the set of these particles, so it only has the properties which those particles have in common as definite properties. It has no definite trajectory. That's the idea. Yeah.